Thank you very much, Marco, for the invitation and for the very detailed introduction. And so I'm very happy to give this presentation about quantum computers in theory and in practice. So this will be a very introductory presentation, keeping in mind that some of the people listening are not experts, and also maybe they could not even know at all what a quantum computer is. And so I will really start from the basics. And so this is the outline. I would like to speak about these 4 main points. So what is a quantum computer in theory? So the ideal model of a quantum computer, and what problems they are able to solve, and importantly for this community, what kind of implications they have for cryptography. And then I will also speak about quantum computers in practice, because as you probably know, in the last 5-10 years, there has been a kind of explosion of technology and a lot of progress in this field. So maybe you are interested in knowing what is the current status of quantum computers. And maybe something to speak about is what kind of problems we can solve today with the noisy and small-scale quantum computers that already exist, and how far we are from the ideal quantum computer, which is presented in the first part of this presentation. So let me start with what is a quantum computer in theory. If we can maybe summarize with a single sentence what a quantum computer is, we can say that it is a physical machine. It is important that it is a physical object that intentionally uses the laws of quantum mechanics to perform computations. So you can think of very simple workflow in which you have some input classical data. This is, according to this input, a given quantum systems, like a set of atoms or circuits, superconducting circuits, is prepared in a quantum state that depends on the problem that you want to solve. The system is measured in the end, and the measurement produces a set of classical data, which is the output of the computation. So you are using a physical system to perform computation. And it is very important that so that the quantum computer uses the laws of quantum mechanics intentionally. So we really make use of them, not just that you need quantum mechanics to describe the components of the computer. And what are the components of the computer, of a quantum computer? Usually they are quantum systems. There are a lot of different backends, but you can think of atoms, electrons, and photons as kind of 3 main good candidates for storing and processing quantum information. And we will come later to practical implementations, but for the moment, you can think of physical systems like this. And as I said before, it is important that even the abstract computational model is based on quantum mechanics. Because maybe you could argue that even a classical conventional computer works with transistors, semiconductors. These are like components that if you want to study them from a physical point of view, you need quantum mechanics. On the other hand, it's just a technological aspect. So the abstract computational model of a classical computer is independent from the physics. A simple test to check if you have a quantum computer or not is if you can replace the components with fully classical analogs. For example, you take a transistor. This is in principle a semiconductor. Maybe there are some strange quantum effects going on, but a transistor could be safely replaced in principle by a completely classical device in which you just have a simple water valve, and nothing will change in the abstract computation of the classical computer. So what is this abstract computational model that a quantum computer has, which is different from the classical one? Let's try to understand this aspect. So as you, of course, know, the elementary unit of a classical computer is a bit. So the elementary unit of information is something which can be in two states, 0 or 1. And the computation is based on operations applied to bit strings, like functions of bit strings to bit strings. And readout of the results is very simple. You just read the status of your memory, and this measurement has no consequences. You can measure as many times as you want. You can even copy states and so on. On the other hand, the quantum computer is based on an elementary unit of information, which is called a qubit. And the qubit is like a classical bit, a system that can be in two distinguishable states, 0 and 1. You can think, just to have a picture in mind, an atom that can be in the ground state or in the excited state. So two distinguishable states, but because of quantum mechanics, we know that the real quantum state can be any arbitrary superpositions of distinguishable states. So in practice, a quantum qubit, the state of a quantum qubit, is a linear combination of 0 and 1 with complex amplitudes alpha and beta, which are normalized to 1. So the absolute square of A alpha plus the absolute square of beta is equal to 1. This is already a bit more complicated than a single qubit, than a single bit, because you need more parameters to describe even a single qubit. And operations now are unitary transformations applied to qubits, which means that, I will explain later mathematically, but in practice, from a physical point of view, it means that states evolve according to the Schrödinger equation. Again, as you can see, that these green parts of the slide are related to physical principles. And these physical principles are directly reflected on the computational model. This is why you can't replace a component of a quantum computer with a water valves, as it was in the previous slide. So what is the readout? This is an important difference from a quantum computer and a classical one. So even if the state is something like this, so quite complicated, depending on a lot of parameters, when you try to measure it, you always get a binary outcome, either 0 or 1. And the probability of getting 0 is given by the absolute square of alpha, and the probability of getting 1 is given by the associated coefficient. So the readout is non-deterministic. And another important aspect of the measurement is that the measurement itself changes the state of the memory. So if you measure, for example, a single qubit and you get the outcome 0, the state becomes, after the measurement, the state 0 with amplitude 1, which is called the collapse of the wave function in quantum mechanics. So these are kind of the basic rules of a quantum computer. And probably if you look a bit of like blog posts or things that you can find on internet, you always find a description like this, but it's very hard to understand why this is much more powerful than the classical computer. And actually, even experts don't know exactly where is the magic of the magic feature of a quantum computer that allows a quantum speed up. But a nice way to understand this is to model the computation with a mathematical formalism that I'm going to explain. So before jumping from classical to quantum, it is better to do a kind of a smooth transition going from classical to classical probabilistic computers and then to quantum computers, because this will clarify a lot of aspects. So what is a probabilistic computer? It's something like what we have defined before, but now the state is not just an arbitrary bit string, but it may happen that you don't know exactly what is the state of the computer. And so you can define the state as a probability distribution over all the possible bit strings of the memory. And since if you have n bits, you have 2 to the n possible states. And so you have a very long vector of probabilities, which is normalized to 1. The sum of the elements is equal to 1. And what is the state evolution? So any operation that you apply should preserve the normalization of the distribution. And so if the operation is also linear, as it is often the case when you apply simple gates like control not, for example, you can write the evolution as a matrix multiplication of this input state to the output state, mapping probability distributions to probability distributions. And what are the possible computations that you can do in this way? So what are the rules? This matrix T must be a stochastic matrix, which means in practice that it contains positive elements and it preserves the normalization. So the one norm preserves the one norm of these vectors. And what about measurements? We said before that quantum computers are probabilistic, but even in this model, the measurement outcome is probabilistic. So if you look now at the final state of the computer, you always get around a probabilistic result, Z, which is sampled from the final probability distribution. So as you can see, this looks much more similar to a quantum computer because you even have a kind of equivalent of a wave function collapse, because after you measure, the state changes because now you know I am in the bit string 1111, and so the updated probability distribution changes. So that's very, very similar, but not quantum. Actually, this has the same power of a standard classical computer. So where is the difference? So the main difference is that a quantum computer works with amplitudes and not with probabilities. And amplitudes are complex numbers. In particular, they can have negative numbers and they can interfere. But let's go maybe slowly. Let's try to do the same for a quantum computer. So we have seen that the state of a quantum computer can be written as a linear combination of bit strings, where now these amplitudes are complex numbers. And again, we can put them in a very long vector, again with 2 to the n components as before. But the main difference is this one. The normalization is related to the 2 norm of this vector. So you have to take the square of each component, you have to sum them, and their sum should be 1. So apparently this is just a small mathematical detail, but this has huge consequences on the operations that you can do and on the power of this device. So what is a computation? What is the state evolution? Again, you can write a linear operation as a matrix multiplication of this very long vector, producing another very long vector of complex amplitudes. But now this matrix U is not a stochastic matrix, but it is a unitary matrix. And the main difference, again, is that it has to preserve the two norm of vectors. That's the main property of a unitary matrix. And because of this, it can be shown that you can obtain much different types of computations, and maybe you can solve better problems. So again, the measurement is probabilistic and given by the absolute square of these elements. So this is just the tiny mathematical difference between quantum computers and classical computers. But again, maybe it's not so clear why it helps, And I have to say, I also don't know exactly why it helps, but there is a nice aspect to consider, which is amplitudes can generate interference, while probabilities are always positive, and so they always sum up in a kind of boring way. You don't get strange effects. Interference can give rise to quite strange effects. And I give you an example, which is not really a quantum algorithm, but more or less gives the idea of how quantum algorithms are written. This kind of structure is quite general. For example, assume that you can prepare a uniform superposition of all the possible bit strings in a quantum computer. This is the uniformly distributed state. And this is very easy to do, actually. Now, assume that you perform a computation, and since you have all these components in the wave function, you are applying the same computations to all the possible inputs, at least in the abstract description of this quantum state. So the problem now is, how can we read out the final state of this computation? And here comes a very interesting aspect, that you can try to apply a final set of operations such that you induce destructive interference of bad results and constructive interference of good results. So you try to amplify good answers and attenuate bad answers. And this is possible thanks to interference effects, because amplitudes can cancel each other. And then maybe you get the correct answer, and it is easy to measure because now you have just a limited number of components, maybe even just one, and so you can get a good result. So what is the main advantage of using amplitudes is probably related to this interference effect. So you can do much more things if you're able to reduce the number of possible outcomes using interference. Okay, this was a quick overview of quantum computing in theory. And maybe if you have questions, of course, you can always ask. But otherwise, I can jump to the implications of quantum computers for cryptography and maybe more generally. So let me go here. What is the most famous quantum algorithm? This is known as Shor's algorithm. And it's an algorithm which is able to factorize large numbers. Let's try to be more precise. Given an integer number n, which is the product of p and q, which are two prime factors, find p and q. That's the problem. And we know that the best known classical method scales exponentially with the number of bits. And on the other hand, verifying a solution is very simple. So these are kind of one-way problems, one-way functions, which are very good for cryptography. And actually, this kind of factorization problem is at the basis of many cryptographic algorithms, as you probably know much better than me. And the reason why cryptography works is that it is very hard to find the prime factors of very large numbers. And what instead a quantum computer could do is you could run Shor's algorithm and you could factorize a number in a polynomial time. And so you could have an exponential advantage with respect to classical computers. And what is more, you can put in a very difficult situation or a large part of cryptographic algorithms. So let me go to the second most famous quantum algorithm, which is Grover's algorithm. This is similar to searching in a database, but so mathematically it works like this. You are given a black box function, so a device that computes something like f, a function of a bit string z. And the outcome, you have this promise that the outcome is 1 only for a particular bit string z prime that we don't know. Otherwise, it is always 0. And so the problem is to find this input z prime that gives the outcome 1. And so if the number of possible inputs is 2 to the n, so if you have n bit inputs and 2 to the n possible combinations, it is easy to guess that the best strategy that you can do classically is to just try with a brute force search until you get the result 1. So the complexity scales linearly in the number of big N, so the number of possible inputs, while it can be shown that using a quantum strategy, you can gain a square root advantage with respect to the classical complexity. So this is a weaker type of advantage. It's not an exponential advantage, but still square root of a very large number is much smaller than the very, very large number. So it can be quite useful anyway. And unfortunately, it can be shown that that's the best thing that you could do to solve this problem with a quantum computer. So it's polynomial, not because we didn't think in a better way. It's really the best thing that you can do. And this was Grover. So these two are, of course, both related to cryptography. And let's start again with Shor. What's the problem with Shor? Shor could break most existing public key cryptographic algorithms. In particular, all those methods based on integer factorization, discrete logarithm, and elliptic curves. So basically, the majority of public key asymmetric algorithms. Moreover, this is a very important aspect. There is a retroactive risk. So what does it mean? It means that even if you cannot apply Shor's algorithm today, you could still store like sensitive data, encrypted data, in order to be decrypted tomorrow in the future when we are going to have maybe a quantum computer. So even if this will happen maybe very far in the future, encrypted data with these methods are dangerous because they could be decrypted in the far future. And so what are the possible solutions to this problem? So are there countermeasures that we can take? And there are two very different approaches. One is using quantum mechanics again, even to perform cryptography. So to share a secret key, you could use quantum systems like photons. And this is very hard to implement because you need quantum links, quantum infrastructures. On the other hand, the security is kind of perfect in the sense that it is based on the laws of physics. So it is impossible, if built in a good way, it is impossible to attack. And on the other hand, you could try also to use post-quantum cryptography, and most of you are very expert of this field. I know very little actually, but the idea here is that you could still use classical channels, but you could apply different cryptographic schemes which are more robust to quantum attacks. So there are other algorithms which work, and so in this case, the security is based on several theoretical and cryptographic assumptions. But these assumptions, I have to say, are very reasonable. So it's very likely, which is hard, to attack this kind of problems. So these are two very different strategies, and both are potential solutions to this problem. So what about the implications of Grover's algorithm for cryptography? So Grover algorithm could weakly undermine symmetric cryptographic algorithms, because you could have this square root speed up in each kind of brute force exhaustive search of solutions, collisions attacks, functions inversion problems, which are more or less all types of attacks in which you try, for example, all the possible passwords until you get a good outcome. And again, data encrypted in this way are subject to retroactive risk. On the other hand, the way to solve this problem, in principle, is just to double the size of the secret keys. So you double the bits of all secret keys, for example, of all hash values of hash functions, or all the kind of keys that you can have. And since the best advantage that you can have with a quantum computer is a square root advantage, you are already in a safe situation. So this is maybe technologically still important, because doubling the size of a key is not so nice, but it's possible, and it's not so dangerous as the situation for public keys. And I think, okay, now that's another slide on other types of relationship between quantum computers and cryptography. So we have talked about this competition of cryptography against quantum computers. One tries to break the other, but actually there is kind of good cooperation of possibilities. Like you could try to use a quantum computer to produce certified true, fundamentally random numbers to be used later for cryptography. And you could use classical cryptography to encrypt a quantum computation. So maybe people using a quantum computer don't want their data to be publicly shown to the company of the quantum computers, for example. This trick is known as homomorphic encryption, which is present both classically and quantum, and that's a very interesting research field. And also, all the theory of classical codes are at the basis of quantum error correction. This is not cryptography, but highly related to cryptography. And finally, very interesting aspect is that one could use cryptography to verify and test quantum computers. Let me do a very simple example. Assume that I claim that I have a very good and perfect quantum computer of 1 million qubits. Then what you could do, you could give me a very large number and ask, why don't you factorize this number? And if I give you the correct answer that you can easily check, you can verify that I really have a good quantum computers. And so all these kind of cryptographic functions, which are very hard to compute in one direction and easy to compute in the other, could be used in this setting. And this concludes this first part about quantum computing in theory. and also about the relationship with the cryptography. But let's see what is in practice a quantum computer today. What can we do today? And so the first message that we should be aware of is that noisy, small prototypes of quantum computers already exist, and there are actually a lot of them. All the companies and academic institutions that you see here, each logo basically is an example of one of these quantum computers based on atoms, or maybe superconductive circuits, or maybe photons. And this list also is not complete. I just took some logos online, but there is much more variety of implementations. And that's the first thing to know. The second thing to know is that those computers, since they are a prototype, those companies and institutions tend to give them to researchers and sometimes even to users for free, like for example IBM, such that you could already try to experiment and test quantum algorithms on real quantum computers. And in practice, so by the way, this was one of the first online platforms in which you could literally design circuits, placing gates, and run the computation and get the outcomes. But nowadays, if you want to use something more interesting, you can literally program quantum software. So you could write programs using quantum software libraries. Usually they are Python-based, but not all of them. And mostly of these libraries and languages are open source. So that's a very nice aspect of this kind of research field. And you could pick one of those, write down your program directly, and see the outcomes of the computation. So maybe later, I also have a notebook. If we have time, we can see what really means to write down a quantum program. But I don't think we have enough time. So I will go on here with the only slide in which I want to speak about, yes, what I do and what my institution, which is Unitary Fund, is doing at the moment. So as I said, most of quantum software, and actually some parts of even quantum hardware, is open source. And so there is a kind of large open source ecosystem, which is rapidly growing in this field. And Unitary Fund is a nonprofit which helps create a quantum technology ecosystems that benefits the most people. So we try to be kind of intermediate layer between maybe academics, companies, and users. And in practice, what do? We run a microgrant program in which we give microgrants to usually students or anyone who is interested in doing a small project in quantum software and quantum technology. We host community events like hackathons. And by the way, we currently have a running hackathon, and you can check at this website. If you are not an expert of quantum software, that's perfect for you because you don't need to know anything, and you can have a look. And other things that we do is to develop quantum software libraries like MITIC, which is a quantum error mitigation library, or Metric, which is a web platform for community-driven quantum benchmarks. So after these quick kind of advertisements, I just leave you with the link. If you are interested, you can go to unitary.fund and see all the details. But we can come back to the physics and to quantum computers. But I think it's good to know that there is a lot of lively progress and institutions in this field. So what problems can be solved by these near-term computers that we have today? So what is the problem of the computers that we have today? So in practice, all existing computers are still very small and still very noisy. So just to give you a figure of merit, most current circuit-based quantum computers have less than 150 qubits, more or less. And moreover, these are just the physical qubits. But how clean a computation is? So what happens if I run a big circuit on 150 qubits? Most likely you get noise out of it. And so in practice, beyond 10 qubits, these computers tend to be dominated by noise. And that's very bad, of course. So exactly for these reasons, they have even been given a name. They are being called NISQ devices. And often you see this acronym, NISQ, which means noisy intermediate scale quantum devices. And so the question is, what is the computational power of NISQ computers and how far they are from an ideal fault-tolerant quantum computer? So what kind of problems we can solve? Let's see what we can do. So before I go to these points, the first message is the nice Shor's and Grover's algorithms, which are very nice and clean in the theory, they are not applicable at the moment. They need too many clean qubits. Usually you need 1 million qubits, so there is no hope to apply them at the moment. On the other hand, you could try to solve quantum chemistry problems like finding the energy spectrum of molecules, simulating quantum dynamics. This could be used, for example, to simulate high energy physics, or solving optimization problems. For example, we could try to solve max cut problems on a quantum computer with the time that it requires. I'm not making claims about efficiency and advantage at the moment. So current computers are still too small to be competitive with classical methods, even for these simplified problems at the moment. The good news is that people expect these problems to be solved by quantum computers in an efficient way in the next, say, more or less 5 years. Of course, the error bars here are very large, but we are going to reach a regime in which probably quantum chemistry simulations using a quantum computers is a reasonable type of computation to be done. On the other hand, something important to highlight is that there is not a very clear theory of the computational advantage of noisy devices. So all the theorems that we have seen before, like the scaling of Shor algorithm, Grover algorithm, are based on the idea that computer is perfect. If you have a little bit of noise, the risk is that you lose all the exponential advantage of quantum computers, but maybe you can still solve useful problems faster than classical methods. That's the idea of NISQ computers. And okay, what about, these are useful problems maybe. So problems that could be of interest to society and to companies and governments. But what about artificial problems that we could try to define just to check if your quantum device is more powerful than a classical computer for those specific classical problems and artificial problems? So what is an artificial problem? Just to give you an idea, these are the two most famous artificial problems that you could define, like preparing a random circuit that produces a random state, and the problem is sampling from the output distribution of the measurement outcomes of this state. The second problem is equivalent to this, but it's based on Gaussian photonics modes, but it's exactly the same concept. And In these particular cases, it has been shown both theoretically and most importantly, experimentally proved that a quantum computer can be much more powerful, exponentially more powerful than a classical device. So here are, like, I guess, 4 examples of quantum supremacy experiments. Maybe there are more, maybe some of those will be falsified in the future, but more or less all the scientific communities agrees that these quantum supremacies have been achieved, which is a very encouraging aspect. So at the moment, we have machines that can compute things that will take thousands of years of computations on supercomputers built on classical methods. So we have already an advantage. The problem is this is a useless type of advantage because it is defined for artificial problems. But on the other hand, this demonstrates that maybe if you have this strong advantage here, you could have some hope of getting some advantage even for useful problems. So what about the nice algorithms that we have seen before, those that can put in danger cryptography, like Shor's and Grover's? So the first message to take home is that it is impossible to run Shor's algorithm, Grover's algorithm on NISQ computers. Let me be more precise. Of course, you can try to run them for small size problems, but here we are speaking about doing something which is hard to do classically. And so you need to factorize very large numbers. And to do this, you would need millions of qubits and a fault-tolerant quantum computer. So it is very hard to make predictions for a fault-tolerant quantum computer. So before I say that the next 5 years, we could see some applications of near-term quantum computers, actually, I believe something like this. But it's very hard for me and actually for everyone to make predictions on this second step. So the step in which we are able to have error correction, fault tolerance, and large quantum computers could take 30, 50, 100 years, nobody knows. Sooner or later, it's going to happen. This is what most people think. And something to keep in mind is that in 1953, this was the idea of a computer. So it's very hard to imagine what can be the progress in the next 50 years or 100 years. So is classical cryptography secure? For many years, everything will be okay. However, let's always remember this symbol, so the retroactive risk. Data which is safe today could be decrypted in 50 years or less. That's the main problem. So to conclude, I think I try to give an overview of what is a quantum computer in theory and in practice. And what we learn is that in theory, quantum computers are very powerful. They are so powerful that they could break most existing classical cryptographic schemes. In practice, we have NISQ quantum computers, noisy devices, which are quite powerful too, because quantum supremacy have been experimentally demonstrated. On the other hand, this power is not enough to put in danger classical cryptography. So let's always keep in mind this problem. And let me end with just 2 open questions, for which actually I don't know the answer, at least for the first. So can near-term noisy quantum algorithms be designed, be invented in the near future, which could run on these noisy devices that we have today, such that we can could attack cryptographic schemes. So let me explain this better. We know that Shor's algorithm is not reachable in the near term. It requires a perfect quantum computer. But these noisy devices are still quite powerful. Can we invent different algorithms, maybe a bit more heuristic, maybe more, I don't know how to say, but less rigorous, but maybe they could speed up some kind of brute force search or problems like this, which could be dangerous for cryptography. And second question is, beyond this competition, again, between cryptography and quantum computers, are there other areas in which quantum cryptography and quantum computing can cooperate? And before I have shown a slide on this with some examples, but maybe there are many more examples to be found in the future. And that, I would like to conclude basically with these two questions and with this conclusion.